Hello everybody, today I want to talk about material integrated intelligent systems from single sensors to learning distributed sensor systems. And I wanted to address the system level approach, crossing the boundary between engineering and computer science. The story behind. The integration level and density of sensors increased significantly in the last decades. The number of deployed sensors increased exponentially. Integration of sensors, analog and digital signal processing and networking created a paradigm shift from passive sensors, discrete passive sensors, to active, intelligent, communicating, interacting sensor networks and clouds. Sensors are now integrated in everything in a device. The next step I want to address here, material integrated sensing and actuation systems, measuring and changing the physical state of structures and materials. The book behind the story. A little bit advertisement. But the reason why I show this book is it clearly identifies the required interdisciplinary research. That means material science, computer science, electrical engineering and electronics, fabrication and integration technologies, and microsystem technologies, and so on, and mathematics, and so on, production engineering, and so on. The evolution of sensors is revolution. There was this transition from passive, discrete sensors to active, connected, smart sensors with an exponential increase of sensor density and number of sensors. This is shown here. Here from the beginning to sensors 4.0, sensor clouds, Internet of Things, connected, crowdsourcing, and so on. But this creates big data volumes and big data too. So this is inherently a consequence. But do we get information and knowledge, wisdom from these big data or these big volumes, big data volumes? This is the question. So we talk about knowledge. How can we derive knowledge from sensor data, and how can we understand sensor data? What is the spatial and temporal context of data? Very important. So we distinguish deductive knowledge. We distinguish inductive knowledge and information mapping. So inductive knowledge is typically a result of data-driven methods like statistical modeling and machine learning. Deductive knowledge is more or less semantic and ontology-driven methods. And information mapping is the bridge between both, basically. Knowledge graphs, for example, can provide relational mapping of data and knowledge and reasoning. But this is important. Machines do not have a priori access to deductive knowledge. So, if we talk about knowledge, we talk about information processing. And digital information processing and network connectivity are fundamental for intelligent systems merging analog and digital worlds. But traditional concepts and algorithms from computer science are not really matching the requirements of pervasive and ubiquitous distributed intelligent systems very well. It's a well-known fact since more than 10 years. So, multi-level, multi-domain and multi-model methods, as well as interdisciplinary research, are mandatory. That's my hypothesis and my experience. So, we talk about adaptive and learning technical systems in relation here to this context here. So, new information processing and communication methodologies are required to master the real world of uncertainty, that means noise, for example, change, dynamic change, continuous change, and failure. Technologies are already available. I will show it next. The methods and algorithms are missing or incomplete to address adaptivity and flexibility of complex systems. So we have basically a hardware-software gap. So let's fill the gap with distributed programming, virtualization, self-star systems, agents, and machine learning, to mention some of them I address here in my talk. So we have a hardware-software gap, and so after the introduction section, I have only two further sections, the hardware technology sections and the software, or more or less the algorithms section. What are the challenges of material integrated intelligent systems? Large-scale and heterogeneous sensor networks and scalability is one challenge and one fact. Big data volumes in real time, energy supply, limited energy supply, energy management, energy storage, and so on, energy harvesting. Sensors and actuators are characterized by noise, drift, unreliability, and inaccuracy. It's very important. It's not a laboratory measuring system. In your smartphone, a sensor costs about $1, and it has noise, it has drift. It's more or less unreliable. Okay, this is okay, and is very inaccurate. So, most important, different to to some smartphones, most smartphones are already affected by this issue too. Limited or no serviceability. If it's integrated, I can't do anything inside. For example, fiber metal laminate plate. No single point of failure, but it's important. Robustness on system level. And finally, integration and host material impact. This is a more engineering issue. So the sensor is a material defect, and the host material has impact on the sensor, including electronics and so on. So you have some of possible applications: structural health monitoring, interactive system, including tangible user interfaces, programmable matter, intelligent objects, robotics and autonomous vehicles, and adaptive structures. It's similar, or it's related to programmable matter. So, for example, adaptive wings or rotor blades change the shape under different operating environmental conditions. Here are some research highlights. The ground base of the MIS discipline, and this is first of all the Interdisciplinary Research Center Integrated Solutions in Sensorial Structure Engineering, and actually current the DFG Interdisciplinary and Trans-Regional Research Unit Ultrasonic Monitoring of Fiber Laminates with Integrated Sensors is more or less the successor of ISIS. So here we see the concept of material integrated intelligent systems. And here you see we have different domains. We have sensor technology, signal and data processing, material integration, networking, communication, energy supply, and we have the interface to the world. And the world play an important role. And so we have to address a lot of questions and methods to create so-called smart sensor nodes. And finally, we have the application scenarios that must be matching the fundamental elements of a material integrated intelligent system. We want to talk about intelligent objects. An intelligent object, is defined by its interaction with the environment and its state sigma. So we have basically a closed loop. We have the world, we have sensing, perception, we have a state change of the intelligent object by computation, and we have finally actuation, modifying the world, and again and again. And the world, that is, for example, the environment, machines, devices, humans, or pure data. So, an intelligent object can be considered as an agent that is coupled loosely to its environment and poses self-star capabilities. That means self-adaptivity, organization, self-organization, self-connectivity, self-learning, self-mobility, self-management, self-improvement, self-diagnosis, and awareness. And all these features can be features of agents or multi-agent systems. So self-star capabilities are considered as enablers for future computing systems that will have to deal, that means learning technical systems, with unprecedented complexity, heterogeneity, and dynamics. So self-star refers to the capability of a system to modify its own behavior or structure without any external control in reaction to even an anticipation of system dynamics, or even an anticipation of system dynamics. Intelligent objects are not limited to sensing systems. It's more or less a mechatronic systems. This is shown here. So we have additionally actuators, and here you see again all the components required. The information processing, communication system, human-machine interface is very important. Sensors interacting with the environment or sensing the environment. Here we basically the system, the basic system. And energy plays an important role in mechatronic systems too. So we have two worlds, digital worlds and analog worlds. Digital electronics and analog electronics. So this is the basic structure of a mechatronic system with sensors, information processing, communication, actuators, and analog and digital systems. So, the technologies. What can we expect? What kind of sensor data and data processing capabilities can be expected? Processing power, data storage. Today, what can be expected in the future. Maybe we can extrapolate that. So the hardware and systems are given here in my talk, and but in contrast to conventional data processing systems and communication, we have to expect failures and to handle them as the normal case, not as an exception. So one example here we see programmable matter. It's more or less now a company. You see it here. It's a very small ball, 4 millimeters in diameter. And the basic concept of this 3D robot called Katom is an electrostatic actuator. So we have here, for example, one ball and a plate and a base system, like the Schwebebahn, yeah. And with electrostatic forces, a movement is created. And if we have not such a base ground operating platform, and we have interacting, in this case 3D robots, we need interaction and self-organization by all the entities if one entity wants to move. In this very small robot, we have a nanocomputer. We have very tiny computer. We have here flexible board technologies with the electrodes and the sensors. We have RFID energy and communication and energy supply with micro cavity storages and so on. So, but what we need is, from the computer science perspective, collaboration, coordination, organization, negotiation. Yeah. This will be clear here, or not. This really it can be seen here. This is from the company, the advertisement material, and they're already identified distributed programming, mobility, regular lattice ordering. This is based on the concept. I can't show it here. It's because the video is not working. But if one of these balls will move, it needs interaction with the other balls, the other catoms. Yeah? So neighborhood communication, message sending is very central. But higher levels of structural organization is required. Maybe I can show the so here you see it. This is basically the animation, the concept. Yeah, here you see the one moving catome, and this requires, you see it here, the interaction with the other catomes, the other 3D robots. This is the theory. Now reality is coming. This is reality. Oh my god, this is all. Only 2 experiments. The smaller ball, okay, it's moving, but not clearly, the direction is not clear. Okay, you see, many things have to be done on computer science, on the computer science level, to have a meaningful, to satisfy their concept, what they're shown in their animation. Yeah? So theory and practice is still wide, with a wide gap. Here another thing, smart dust is autonomous sensing and communication in cubic millimeter. It's older work, 2002, from Barneke and his colleagues. And you see a fully equipped sensor node called sensor mode, with a battery is the most biggest part, with energy harvesting by light, communication by light and by radio wave, and a fully equipped computer. Here you see another thing is called Smart Dust 2 from Hitachi from 2008, but it's not really a sensor. It's just, you see it here, a read-only tracking device providing by RFID 128-bit user unified identity. But you see the volume. Here we have the volume about 10 cubic millimeters. Here micro millimeters. Cubic micromillimeters. It's very small. And imagine the chip will not send the identity. It will have a simple sensor. Then we have something that we call smart dust. Another example from my colleague Maurizio Valle from University of Genova is the tactile skin. And this is an example. This was an example here for large-scale networks. This was an example for self-organization. And this is here, the tactile skin is an example for hierarchical bottom-up design and hierarchical bottom-up communication. Here you see it. The skin is formed by scalable meshes of flexible triangular modules with a hierarchical design and communication architecture. And here are some details. Here we have the triangles with a sensor array, and they can connect it arbitrarily and form arbitrarily shaped skins applied to structures, robotic structures, and so on. You see different areas addressed, and here the high-level areas, context, deduction, control, and so on. So this is an example for hierarchical bottom-up design, a holonic principle. This is one of the main methodologies I advertise here, the holonic principle. And finally, structural health monitoring, with different integration levels. Still mostly, you see it here, just integrated sensors and all the wires coming out. If you have thousands of sensors, you have really an issue. But with external diagnostic hardware and analysis software. Here, the next step, full sensor nodes and full sensor networks. And finally, here a foil, a stretchable multimodal sensor network on a foil. And these technology, this sensor on foil and so on, that was shown here, and sensor in foil technologies are already available. So this is the technological ground, yeah? And this is enough to talk about self-organizing systems. But computers and data processing, what can we expect? But even a square millimeter computer provides today enough capabilities to perform machine learning, for example, TinyML. We can expect about, only rough figures, about 100 mega instructions per second per square millimeter. 100 kilobit memory per, only roughly, per square millimeter. 100 microwatt per square millimeter and 100 kilobit per second communication. That can be typically expected in such tiny embedded systems, depending on many factors, of course. So here's an example we are already using in our research group, the ARM Cortex M0 Plus, 1 MIPS per megahertz, typically controlled with 1060 megahertz, or clocked with 60 megahertz, about 10 to 100 microwatt per megahertz, depends on the silicon process, 8 kilobyte RAM, 32 kilobyte ROM, and about, this is very tiny, 0.01 up to 0.1 square millimeter already. Again, depends on the silicon process. So it's well suited for material integration. Communication, in contrast to large area sensor networks, distributed sensor networks, here we have wired technologies, often optical using light fibers, or electrical using metal or carbon fibers or carbon wires. In CFK structures, for example, it's possible. And wireless, of course, is used, basically magnetic fields or RFID. Wi-Fi, Bluetooth, this is questionable in material integrated systems, maybe, maybe not. The network topology, this is important. Bus systems are used. Here, for example, they use a CAN bus on some level. 1D, 2D, and 3D mesh grids, very suitable for material integrated intelligent systems. But mostly they pose dynamic communication graphs, typically with short-range neighborhood connection. This is very important, and this is good. So now I come into the third section, methodologies. What can we use for software, and which kind of algorithms and methodologies and architectures we can use? And I call it the low-carbon age. This is the starting point. That means data processing and communication are limited by resource constraint and harsh environmental conditions. That means low computational power, low energy, low continuous processing times. That means due to energy shortcomings, due to limited energy, the processor can only compute 1 millisecond, and then energy must be harvested, and after 1 minute he can compute again. This is meant here by continuous processing times. Low data storage capacity in RAM and ROM. Low range communication. low bandwidth, memory, communication, low reliability, low accuracy, and not only because we have to use a very simple sensor, only a 8-bit ADC, for example, addressing specific energy constraints too. Data width is limited, and data types. The ARM Cortex M0 has no floating point unit. And we have low serviceability. So, virtualization is the first methodology I will address. What? Never virtualize on low resource platforms, you will say. Of course, but we need it. An example. Here you see from our research group, current work. Here with sensor node with RFID communication and ultrasonic sensor. And this will be integrated here in a fiber metal laminate structure. So on the top and on the bottom we have aluminium plates. Or other kinds are steel, for example, other materials are steel. And they integrate this sensor node. It's relatively tiny, but they integrate it in the fiber layer, the preg layer, by cutting out. Cutting out some part, and then they lay the electronic system. Some parts are chip thinned and prepared, but they're not using any flexible board or anything. They integrate it then just in the preg layer, and then finally it's covered by a metal layer. No serviceability, and you can't program the device, for example. If you have one software error in your software, you have to use a saw to come closer to your device. So, here you see an example of an SHA MIST system in a fiber metal laminate, and the most important part is this here. After, we have only RFID connectivity, not accessible anymore. So, virtualization is basically abstraction and unification of course, the microprocessor instruction set architecture. Multitasking, synchronization, sensors, peripheral devices, actuators, communication and connectivity, protocols, memory and data storage, garbage collecting, automatic memory management, tuple spaces at a higher level abstraction, semantic data, context and location. So that means virtualization transforms one application programming interface to another, but by reducing the complexity. And what are virtual machines are suitable for text-based code processing on such tiny embedded systems like the ARM Cortex M0? Now, Lua is a candidate, but even eLua requires about 64 kilobyte RAM, and here our microcontroller has only 8 kilobyte RAM. So another approach is Forth, a stack processor, and we're using MiCrisp. It's not from us, but we're using it, and it only requires at least 1 kilobyte RAM and 16 kilobyte ROM. So it fits very well and it's totally programmable via the RFID communication afterwards. And so we have only to ensure that the Forth engine is running correctly, and if this is the case, we can integrate it in the material. And interesting, MiCrisp has just-in-time compilation. That means it transforms or it compiles Forth instructions to machine instructions, ARM instructions on the fly. So we have only a low friction, 1 to 10. Yeah? It's 10 times slower than C code. Agents are the second methodology I propose, and agents can represent physical entities, digital twins, simulation, can be used for planning and optimization, or can be considered as a distributed programming and communication model. And that's the point here. So agents provide virtualization too. An agent is a micro VM loosely coupled to the agent processing platform. So we address here, and I did it in the past more than 10 years. Agents mean here mobile code, mobile reactive and state-based agents that are used for distributed and unified sensor processing in strong heterogeneous environments. And I address all these methodologies: agent-based modeling, agent-based simulation, agent-based computation, this is the thing here, agent-based learning, and combination of them. ABX, for example, coupling crowd sensing with simulation, agent-based simulation. So here you see a lot of things that can be done by multi-agent systems. I have done in the past 10 years: sensing aggregation, sensor processing and data analysis, applications, structural health monitoring of course, crowd sensing and smart city, chatbots, and so on. control and optimization, adaptive and robotic materials, simulation, parallel distributed traffic and smart city, human and real world in the loop. That means combination of crowd sensing, agent-based crowd sensing with agent-based simulation, and multi-domain simulation, coupling agents with multi-body physics. So here are two prominent agent platforms I have developed and investigated in the last 10 years. It's just a tool. It's not a revolution. First of all, the JavaScript agent machine, entirely programmed in JavaScript, can be embedded in any host application, including web browsers. Agents are mobile code, and it relies basically on the tuple space communication model, but it requires about 2 megabyte RAM, 2 megabyte ROM, and so it's not suitable for material integrated systems. But there's another machine, the agent fourth machine. Again, we are using fourth, but a specialized multi-threaded or multi-stack processor. And there, from agent fourth, there are hardware implementations using FPGAs or ASICs basically too, and software implementations, C, NoCaml, JavaScript, and so on. Suitable for tiny embedded systems with a multi-threaded stack processor, and agents, again, are also mobile code, and the requirements fit to material integrated systems, not to the ARM Cortex M0, but 100 kilobyte RAM, 200 kilobyte ROM, or 1 mega equivalent gates with an FPGA ASIC design. So you see two examples here for the agent fourth machine. Here we have a prototype of a sensorial material, but with an applied sensor networks, applying strain gauge sensor to a rubber plate, to a flexible plate, elastic plate, with a 2D mesh network of sensor nodes with FPGAs. And here we used the agents to perform distributed sensing and robust sensing under failure constraints and so on. Finally, performing machine learning to predict an applied load, and both the class of the load, that means the weight, and the position. On the other side here we have an example of multi-domain simulation using here a three-dimensional GEM network in simulation. And interconnected, and the agents fulfill self-organized and a self-organized optimization problem by adapting a material to react on loads and defects. Here you see holes. This is holes in the structure, and the agent or the multi-agent system tried or succeeded to solve a distributed optimization problem by minimizing the entire strain energy of the structure. Yeah, and finally, or not finally, but the most important part, distributed learning and TinyML. And here again we have the principle, the Holonic principle, with decomposition of large complex problems in multiple simple problems. That means the divide and conquer principle, and distributed local data processing. And here you see the basic concept. We have again we have a network of sensors or sensor nodes, specially distributed, but the traditional case is we collect all data and have one machine learning model that performs, for example, damage prediction, localization of damage, and so on. Now, the transition is we have a local learning on local data with multiple models that are fusion globally. This is the main concept here. From single instance centralized to multi-instance distributed multi-model machine learning with global fusion. Here's an example of such a sensor network from our research group. And here you see a lot of sensors or sensor nodes. And we use ultrasonic signals from guided ultrasonic waves to detect damages. And here, each sensor has only the local sensor signal and tries to predict, is there a damage nearby or not. The cross is the damage applied to the structure. And you see here we have different experiments. Here we have a very strong indication. All these nodes which are red have clearly identified an damage, predicted damage. Here we have a weak case, but still one node is very strong. And here we have artifacts. So these are false positive indications here again and here again. But by global fusion using density clustering and probabilistic filtering, we still get a relatively high robustness in the prediction of damages and their localization. Yeah, and finally, my last point, algorithmic scaling, how to fit in embedded systems. And here the main principles are decomposition and distribution, already shown, downscaling, that means reduction of data complexity, data accuracy, algorithmic complexity, algorithmic substitution, approximation, model-based approaches, including model reduction and model substitution, and of course accelerators in hardware and software, coprocessors, high-level synthesis of algorithms from software to hardware and RTL. Here we have an example to conclude. Here we have this ultrasonic signal, and you see here the difference between the baseline and the damage is very small difference in the signal. And initially we used discrete wavelet transform to get features from the signal and a relatively complex state-based long short-term memory artificial neural network to detect the damage from the time series prediction. We required about 1 million instructions and 500 kilobyte memory. Then my colleague Christoph Bolle investigated it by physical modeling and identified that the peak and the peak value and the width of the hull of the peak, here you see, and its position on the time scale is enough to identify a damage. Yeah? And so, by computing the hull and some maximum search and fitting with finally a discriminator and additional temperature scaling by numerical methods, simple analytical models, he can predict a damage too. The only problem was the hull, computation of the hull by the Hilbert transform and providing an analytical signal. This is very time consuming by FFT, and we solved this. This is an example for model reduction by using a rectifier and a simple first order low pass filter. And then we have only 10 kilo instructions by 5 kilobyte memory. Okay, summary. The design and implementation of material integrated data processing systems is a challenge. I showed it in terms of susceptibility to errors, low performance per node, large scale networks, energy supply. In contrast to the internet, which is still primarily administrated by humans, MIS requires self-staff features and self-organization. There's also a big hardware-software gap, and possible methods are introduced to summarize virtualization, multi-agent systems, distributed sensor data processing and ML, algorithmic scaling, and model reduction. Thank you for your attention. Any questions?